Let's go through the whole action potential now. And now what I want to do is also plot this out. Here's time. And the units are going to be milliseconds. In other words, thousandths of a second. And on the y-axis, we have in millivolts, I'll put minus 100. Remember, that's the equilibrium for potassium. We'll put minus 80. Oops, minus. Try that again. Minus 80, which we get to in the dip, the undershoot of the action potential. Minus 70, where we start. Minus 45, which is threshold to open voltage-gated sodium channels. And way up at the top here, I'll put plus 50, the equilibrium for sodium, and plus 30, where a typical action potential goes. So let's trace through what happens. I'll talk about it, and then we'll sketch it out. So here we are at a typical membrane potential. Some positive charge coming near voltage-gated sodium channels in an axon need to bring it to minus 45. So this part is positive charge getting to that point. At that point, voltage-gated sodium channels open. That allows a lot of sodium into the cell, and we get up to about plus 30. Up at the top of the peak, the voltage-gated sodium channels close their inactivation gates. So picture that. The inactivation gates close because of all that sodium, and voltage-gated potassium channels open. Remember, potassium will leave the cell until you get to minus 100. If a positive ion, a cation, is leaving, the cell ought to get more negative, and so we get more negative, and we go down past 70 because we have voltage-gated potassium channels and potassium leak channels open. But we don't go all the way to minus 100 because there's still a little sodium coming into the cell. Then we close those voltage-gated sodium channels, voltage-gated potassium channels. We close the voltage-gated potassium channels, and now we're back to what we started, and we drift back up because of the sodium coming in to minus 70. So this last part is the combination of sodium coming in through secondary active transport and some other ways, and potassium leaving through leak channels. We're back to where we were, but remember the refractory period in which you can't get another action potential. At this point, we have voltage-gated sodium channels with their inactivation gates closed. Their activation gates are open. Over here, they're now with their activation gates closed and their inactivation gates open. So at this point, finally, we'd be ready for a new action potential. So we can get a new action potential possible . Make one last comment. These inactivation gates don't all pop open at exactly the same speed, and so it's not as if there's one point in time where suddenly a new action potential is possible. What happens is, over time, one by one, these voltage-gated sodium channels go from inactive to active, and at the point where enough of them are active, you can start a new action potential. When they're all active, you're completely back. When they all have the inactivation gate open, you're back to when it would take the typical minus 45 to start an action potential.